Hope this morning's sessions were enjoyable. Certainly we had some very good speakers in here, and the breakout group I was in seemed to have gone very well, and the feedback from the others has been good. So thank you for the leads in those speaking groups, in those breakout groups. And it is something that we've tried that's slightly different to try and break up the day a bit, to bring a bit more variety. And some of the feedback we've had from previous years is just a whole day of being spoken at just makes it a bit long and tiring and distracts from some of the speakers later in the day. So hopefully you're back in here refreshed and looking forward to some really informative talks this afternoon. So I won't carry on for any longer, but we'll introduce our first speaker this afternoon, or first speakers, Mark Hanham and Chibuzor, both from RSSB, and they're going to talk about smart traction energy management, and particularly some work that's been going on the Great Western. So Mark works as a senior research analyst at RSSB. He joined the team in 2019 for an industrial placement while still studying for a degree, and he returned after graduating. So, Tom, maybe you're not the youngest presenter here today, but welcome anyway, and it's good to have some age variety and diversity as well as a wider diversity. And then Chib works as a principal energy engineer at RSSB, and he's had a mixed career working in maintenance, project delivery, as an independent assessor, and now in standardisation. And within each role, he's provided insights into challenges of electrification. So he's got electrification running through his career, but with a wide range of roles. A personal achievement has been his involvement in the revision to the AC standards and the estimated savings that they have brought to the industry of potentially £27 million over 5 years, whilst also contributing to the carbon emission reductions, particularly by promoting modal shift to electric freight and to electric freight trains. So I'd like to welcome Mark and Chib to the stage to give their presentation. Thank you.
Thank you very much, Paul, and thank you, audience, for coming. It's always a challenge, isn't it, after the lovely lunch, and particularly so on this particular subject. But you get two for the price of one. So Mark and I are going to be talking to you about, it is quite a esoteric, abstract subject. I was thinking about this, and I thought, actually, this is all about PWI. PWI, Power Demand Management. That's your P. W, Western route, and then the I, in real time. So there you go. If you can remember that thread going through this presentation, hopefully we can take you on a journey. I was reminded just the other day that this particular subject runs through all our lives. I made the dreadful error of buying 4 pizzas, and there were 5 of us. My wife wasn't there, 4 kids, and they each wanted a pizza. So out came my power demand management tool, the scissors. So remember that one going forward. I will hand over to Mark. Mark will take us on a journey about halfway through, and then it will seamlessly pass on to me, and I'll finish things at the end. Thank you.
Wonderful. Okay, thank you, Chib. Hello, everybody. And I'm just going to start my little part of the presentation by just setting the scene for RSSB, why we do research, and why this project is research for us to do. So, there we go. So, why the research programme? What is it? So, RSSB's core work in standards, in system safety and health, and in sustainability has been running for many years, as has the research programme which supports our core work. Our work focuses on system interfaces, areas where the different organisations each have a role to play to promote improvements to performance, railway safety, process improvements, and as you can see on the slide, our areas, key points to focus on is projects that optimise railway operations, that make incremental changes to systems and processes, and unlock a fundamental change. And examples of our work we've already had mentioned in Tom's presentation about DC electrification, T1214 study on 21st century electrification, and I'm delighted that the industry is running with that one. We've also done work slightly more recently that finished earlier this year around battery trains, their introduction, around their operations, charging hierarchy under code T1272. Today, though, is all about T1270, feasibility of smart structured energy management on the Western route. And as it might seem obvious, it's bringing in lots of different organisations, from the train operators to the manufacturers of the trains to Network Rail. Bringing them together, collaborating, which is what RSSB does really well. So, the background to the project is fairly simple. There are areas of the network today that have challenges in balancing the supply and demand. Quite frankly, there isn't the supply to meet the demand and to run the electric trains that we would like. Now, these are perhaps only in certain areas and only at certain times. But without an intelligent management system, like the one we're proposing, there is the risk that longer trains, additional paths, and battery train charging could be restricted. So therefore, we're looking to find a technological solution to this problem using systems already on the railway, like the connected driver advisory system, the traffic management systems, and the 61850 standard for communications between substations. Now, at this point, the obvious answer is Western route. As Chib's already said, power demand management in real time on the Western route. All those technologies are already on the route, and while it may not have the constraints on supply that other routes have, it's a good example to have a proof of concept, and we have industry support from our steering group, and I'd like to thank members of the steering group at this point, from First Group, from Great Western Railway, from Network Rail, and from Hitachi. Our delivery team has been Navitas Engineering and Steer, and so we are the mouthpiece for their findings today. So, what exactly are those findings? Well, what we've created is a concept to a system. And you can see the top left graph shows the capacity, the supply and demand problem as it would ordinarily be. The capacity being a fixed line, the demand goes up and down depending on the trains that are running. And so there are times when there's more headroom and times when there's less headroom. The middle graph shows where perhaps capacity is reduced for a certain reason. Maybe there's a fault, maybe it's older infrastructure. There may be good reasons for this, and therefore there is a limit on the trains we can run. So a smart traction system is required to adjust the demand accordingly. Similarly, the bottom right graph is where there's perhaps the opportunity to maybe charge battery trains or run additional electric paths or longer trains in times when we really know there is the headroom, and a system like this is giving us the proper evidence that headroom really does exist. So at bottom left, you can see the types of demand response, the methods you can use, and Chib will talk about those a little bit later on. But quite simply, you can run the train slower to reduce demand, you can have a current limit, not restriction, and of course just change to diesel. But we don't just want to change to diesel, we want to try and reduce the electric but still run on electric. It's really important that this project is enhancing the decarbonisation of the industry and having a cost-effective way of doing it. Top right, final on this slide, is just to say the basic outline of the system, taking data from the infrastructure, going forward into a processing engine, what we've called the Energy Management System, or EMS, going then forward to take an operational decision to regulate demand based on the data we have and based on the forecast. Now, my final slide before I hand over to Chib is about the project benefits. You can see the Venn diagram bottom right, which is showing that there are three main categories of benefits. There are planning benefits, there are disruption benefits, and there are longer term benefits. And just taking a few of these, you can see the list there. I've already talked about running additional paths and longer trains, but this is all facilitated through removing pessimism in modelling and being able to demonstrate with evidence that these things can be run. Similarly, around optimised battery charging, which is perhaps a longer term ambition, and being able to perhaps prioritise services based on their energy efficiency, and that's where the role of electric freight comes in. There's also the point about disruption benefits, where perhaps there is a restriction that's a bit more permanent than we would like, that actually only needs to be applied at certain times, and the evidence can be provided through our system. Now, at this point, I'm going to turn over to Chib to take the rest of the presentation. Thank you very much.
Thank you, Mark. I told you the exchange would be absolutely seamless. So, given the benefits that Mark has just been talking about, and I do hope you've remembered PWI, to just help you right along throughout this presentation. We're talking about power demand management, Western route in real time. So, how do we realize those benefits? Well, we need to know what capacity is. And to do that, as a steering group, we examined what exactly was constraining the system, capacity constraints. And we identified two different categories of capacity constraints: system level constraints and component level constraints. System level constraints are those constraints that affect your feeder area. We're talking about an AC system here, so perhaps from midpoint to midpoint. And then the component level constraints are, if you like, subsections of that feeder area. So we came up with 5 examples, 5 key areas for the system level constraints, which you can see on your screen. Things like voltage, harmonics, right down to system voltage. And then for the component level constraint, the one key area we came up with was conductor and cable currents. So that's, in terms of measuring capacity, those are the key capacity constraints we want to look at. So what is there now to regulate demand on the Western route? I appreciate this diagram looks busy, lots of boxes. This is just trying to show the relationship between the connected driver advisory system and the traffic management system in use right now on the Western route. And the key bits here are those sort of 3 boxes on the top left. You've got network road planning system, you've got network road infrastructure data, and then Illuminate traffic management system, all feeding data to that TTG CDAS server. And what that's doing is it's bringing in all the data. So you have data like line speed, you might have infrastructure data like the gradient, and it works out the optimum speed advice to meet particular timing points. And that's then communicated by 4G 2 different ways. For the Class 800s, that's integrated into the train, or for the Class 387s, that's a standalone device. So that's what's out there now on the Western route. Still with me? So I've talked to you about what's out there on the Western route. What can we do to modify demand? Well, we've got a demand response system. What's that all about? A bit like me going to my doctor the other day. I've got back pains. They might prescribe me a pill or something. That's the demand response. The response mechanism is actually how that's implemented. So thinking about this, the constraint, we have 2 different types of demand response. We've got operational response, things you'll be familiar with. You might change the service length, might change the service frequency. And then we've got onboard dynamic responses, things that we can do to effect demand. Might notch restriction, current limitation, might reduce the speed. So that's the demand response. On the other side, we've got the response mechanism. How is it going to be implemented? 2 different ways. One via this connected driver advisory system to the driver, give some advice, and the other directly through the train control and management system. without a driver, so direct to the train. So what regulation strategies might we use, and how effective are they? Now, apologies, I recognize you can't see those 8 graphs there, not necessarily important for this. So to answer this question, the question we had in our mind was, well, we want to do a simulation and we want to see how effective speed is. So on the left, on the right-hand side, you've got on the x-axis speed, and on the y-axis is the peak 30-minute power. Now, this simulation was just a typical simulation, fictitious, 100-kilometer area, maximum speed, 160 kilometers per hour, with stations at 10, 20, 50, 70 kilometers. And what we want to see was that the effect on the peak power. And as you might expect, as you reduce the speed from 160 right down to 40, that peak power reduces. We also, as you might expect, also noticed that the peak power reduces as you increase the headway. And you can see in those different colors, we had headways from 5-minute headway all the way up to 30 minutes. So results that you might expect. And how effective were the regulation strategies? Now, this graph is busy. Remember, we're talking about PWI, power demand management. We're looking at 3 different methods here to regulate demand. One was speed, current limitation, and then tractive effort, and we're trying to compare which one was the most effective. Interestingly, the take-home here for this was that speed was actually the most effective strategy, which surprised us. So putting the whole thing together, what does the architecture for the regulation concept look like? The system concept that Mark was talking about. Again, bear with me, a busy slide. We've got 3 main pieces of the jigsaw puzzle. On the left is the measurement system. In the middle is your energy management system, my scissors when it comes to the pizza. And on the right, the onboard control. The bits in red are new parts of the system. Bits in blue are modified parts of the system. And essentially what we've got is we might need to add equipment to the measurement system in order to measure that constraint and transmit it to the energy management system. That's our forecast engine. And that energy management system has 2 functions: to predict what the constraint might be, 24-hour and 2-hour look ahead, and then it interacts with the traffic management system. And the output of that is it triggers an intervention. And there are 3 different ways in order to execute that. The top one there is via CDAS. The middle one on the right hand is a modified CDAS. And then the most complicated option is to have an integrated IEC 61850. So the real take home here is that some options, as you go down the list, the table at the bottom, system gets more complicated. Now this is even getting more complicated. So we wanted to understand what the system options were. Now we're talking about the measurement system, remember, that part of the jigsaw puzzle, the energy management system, that bit in the middle, and then the onboard control system. And each of those you can divide into different bits, different options. And the steering group came up with quite a number of options, as you can see. We divided those into different parts, which aligned with the benefits that you see on the right. The key take-home here is, obviously, again, as you go down the list, if you like, the system gets more complex, but the amount of benefits increases. Now, the point of the color coding, really, was to allow us to define 4 different types of systems for the purposes of evaluating the benefit. We needed to kind of, rationalize it a bit. So the 4 systems we came up with, or 4 options we came up with. Option A, your basic system without CDAS. Option B is the enhanced measurement system with CDAS, Connected Driver Advisory System. Option C, again, enhanced measurement system with CDAS, but including voltage and control data from the train. And option D is the most complicated one with an IEC 61850 integrated solution. So, what was the output of the benefits framework? We applied the benefits framework. Mark talked earlier about those three categories of benefits. You've got your planning benefits, your disruption benefits, and your long-term benefits. As far as this exercise was concerned, we were actually quite conservative. The key question we wanted to answer was, well, do the benefits outweigh the cost? Is it actually positive? And for that, an order of magnitude in terms of operating costs at this stage was enough. The analysis only took into account the disruption benefits, but what we did find was that it was positive, so 1.8 pound of benefits for every pound of cost. Again, very, very conservative assumptions there. More details are in the Part 3 report, which is on the RSSB website. So where do we go? I've talked to you about the jigsaw puzzle. You're still with me, PWI. We've got the measurement system, the energy management system, and the onboard control. The view was from the steering group that we want to trial this thing. We want to see how this thing works. And for a pilot scheme, we actually want to make sure that it's an end-to-end system. So not with each individual box that is sitting there, but actually with the measurement system interacting with the energy management system, interacting with the onboard control system. And that's what this is trying to show. This is option B, if you like, of our example earlier, with the measurement system interacting with that forecast engine, which is then triggering an intervention. In this case, we've got the CDAS intervention, with CDAS and the modified CDAS, and we thought the IEC 61850 going full hog with that for a trial would be a step too far, so a standalone device in terms of the trial. So in summary, power demand management, Western route in real time. Mark talked about the system concept. I kind of developed that and talked to you about the regulator concept, and we talked about the trial. So what's the point of all this? Just a few benefits to kind of recap that we talked about. We can squeeze a little bit out of our existing electrification if we have a system like this, potentially avoid unnecessary upgrades, improve performance in perturbed situations, and something that we've heard about earlier in terms of the rollout of battery trains. This can really support that and help the phasing out of diesel-only trains. Everything I've said and more is on the RSSB website. It is published. If you go to the link, I think we'll try and circulate something afterwards. The only other thing to say is a massive thank you. I think you were mostly awake. Again, thank you to Navitas and Steer and all the steering group. There is a webinar, Excitement, on the 19th, so 19th of July this month. I think that's next Friday. Go on the RSSB website to register for that. So thank you very much.